In this video, let us learn how to calculate the maximum speed in level flight. Let us begin with knowing the phases of flight. Any flight flying from one location to another, it has to go through 5 phases such as takeoff, climb, cruise, glide and landing. Here, the level flight refers to the point 3 to 4, that is the cruise phase. In cruise phase, the flight is flying with constant velocity and height to maintain its steady level. For more clarity, consider an aircraft. The forces acting are the thrust, drag, lift, and weight. The thrust force is created by the propeller to move the aircraft in forward direction. Drag is the pull force experienced by the aircraft due to its frictional effect and the air pressure differences. The lift force helps the aircraft to fly, and the majority of the lift is produced by the wings. And weight is a force the aircraft is pulled to the ground due to its gravity. During takeoff and climb, the lift produced has to be greater than the weight. Once it reaches a steady level, the aircraft maintains its height and velocity by balancing the lift with weight and the thrust with drag. So at level flight, as the height remains constant, lift equals weight, and as velocity remains constant, thrust equals drag. Based on the lift equation, the lift is represented as a product of half times the coefficient of lift, density, velocity square and wing surface area. The derivation might look pretty simple. All we need to know is the concept and terms and how and why they are being calculated. In the lift equation, bringing the wing surface area to the left side, L by S is mentioned, and in steady level flight, the lift produced is same as that of the weight. Hence, replacing L by W, the equation W by S is mentioned. With W by S as reference, the lift coefficient and velocity equation is formed. The term W by S, called wing loading, can be measured using the pressure differences. For this, consider an aircraft front view. As the air flows over the wing, low pressure is created on the top surface of the wing and high pressure is created at the bottom of the wing. Product of pressure difference and the wing surface area gives a lift. Replacing the lift by weight, since it is steady level flight, thus the difference in pressure gives the wing loading. For a clear view, let us take the cross section of the wing. The cross section seems to be an aerofoil shape. The front edge of an aerofoil is called the leading edge, and the rear edge of an aerofoil is called the trailing edge. And the line connecting the leading edge and trailing edge is the chord line. And the camber line is an imaginary line which is drawn halfway between the upper surface and the lower surface. Relative wind is airflow direction. Alpha is the angle measured between the relative wind and the chord line. As air flows over the wing, there is low pressure region formed due to the increase in velocity on the upper surface of the wing, and high pressure region is formed due to decreased velocity on the lower surface of the wing. This high pressure created at the bottom moves to the top surface of the wing, thereby pushing the aircraft upwards, resulting with the lift force. This works based on the Bernoulli's principle in lifting the aircraft from the ground surface. For determining the maximum velocity, the coefficient of lift is considered as maximum. This can be inferred in graph. Let us consider the aerofoil with three different angle of attack. The first aerofoil, the angle of attack is minimum. In the second, it is medium, and the third aerofoil has a maximum angle of attack. The flow distribution over the three aerofoil is observed. For minimum angle of attack, the airflow is laminar along the aerofoil shape. In the second aerofoil, the flow is laminar and then it turns into turbulent with minimum amount of drag. In the third aerofoil, the flow starts to separate on the upper surface, leading the whole aircraft to stall. This angle is called the critical angle, and to avoid the aircraft from stall, the coefficient of lift is maintained within limits. This derivation helps us to find maximum velocity at level flight. Thanks for watching, and for more videos do subscribe to IR.